Look around you. What do you see? Tables, chairs, maybe trees or buildings. Now imagine taking one of those objects and cutting it in half, and then in half again. Keep going, smaller and smaller until you can't cut it any further. You've reached the realm of atoms, the fundamental building blocks of everything we see and interact with. Atoms are incredibly tiny, far too small to be seen with the naked eye. Yet these minuscule particles hold the key to understanding the vast and complex universe we live in. From the air we breathe to the stars that light up the night sky, everything is made up of atoms. But what exactly are atoms? What are they made of? And how do they interact to create the incredible diversity of matter we see around us? Let's embark on a journey into the fascinating world of atoms and uncover the secrets they hold. An atom is the smallest unit of an element that retains the chemical properties of that element. Imagine a Lego brick. It's the smallest piece you can have that still represents that particular Lego set. In the same way, an atom is the tiniest piece of an element like gold, oxygen, or carbon. Atoms themselves are made up of even smaller particles called protons, neutrons, and electrons. Protons carry a positive electrical charge, neutrons carry no charge, they are neutral, and electrons carry a negative charge. These three subatomic particles are the fundamental ingredients of all matter. These particles are not just randomly scattered within an atom. They have a specific arrangement that determines the atom's properties and how it behaves. Understanding this arrangement is crucial to grasping the nature of atoms and their role in the universe. The concept of the atom has been around for centuries, dating back to ancient Greek philosophers. Democritus, a Greek philosopher who lived around 400 BC, first proposed the idea that matter was made up of tiny, indivisible particles he called atomos, meaning uncuttable. Historian, however, it wasn't until the 19th century that the scientific study of atoms truly began. In 1803, John Dalton, an English chemist, formulated the first modern atomic theory. Dalton's theory stated that all matter is made up of atoms, which are indivisible and indestructible. He also proposed that atoms of different elements have different weights. The late 19th and early 20th centuries witnessed a revolution in our understanding of the atom. Scientists like J.J. Thomson, who discovered the electron in 1897, and Ernest Rutherford, who conducted the famous gold foil experiment in 1911, revealed that atoms were not indivisible spheres as previously thought. Rutherford's gold foil experiment demonstrated that atoms have a tiny, dense, positively charged nucleus at their center. This nucleus, he discovered, contains the protons and neutrons. The electrons, much smaller than protons and neutrons, exist in the space surrounding the nucleus. Scientist 1. The nucleus is incredibly small compared to the overall size of the atom. If an atom were the size of a football stadium, the nucleus would be like a marble sitting at the center of the field. Despite its tiny size, the nucleus contains almost all of the atom's mass. The number of protons in an atom's nucleus determines what element it is. For example, all carbon atoms have 6 protons, while all oxygen atoms have 8. This number is called the atomic number and is a fundamental property of each element. Understanding the structure of the atom is key to unlocking the mysteries of the universe and the very essence of matter itself. Section 5. Electrons in orbit, a delicate balance. Scientist 2. While the protons and neutrons reside in the nucleus, the electrons are in constant motion around it. Imagine tiny planets orbiting a sun. That's a simplified way to picture electrons whizzing around the nucleus. These electrons don't just orbit randomly, they occupy specific energy levels or shells. Scientist 2. Each shell can hold a certain number of electrons. The arrangement of electrons in these shells determines an atom's chemical properties, such as how it bonds with other atoms to form molecules. The outermost shell is particularly important. Scientist 2. The electrons in this shell, called valence electrons, are the ones involved in chemical reactions and bonding. They determine how an atom interacts with other atoms to form the molecules that make up our world. Section 6. The periodic table, organizing the elements. Scientists have identified over 100 different types of atoms, each corresponding to a different element. Student. These elements are organized in a chart called the periodic table, a cornerstone of chemistry. The periodic table arranges elements in order of increasing atomic number, that is, the number of protons in their nucleus. Student. This arrangement reveals patterns in the element's properties, allowing us to predict their behavior and how they might interact with each other. The periodic table is more than just a chart, it's a powerful tool that helps us understand the relationships between different elements and predict the properties of new ones. It's a testament to the order and predictability that govern the behavior of atoms, even at the smallest scales. Section 7. Isotopes and radioactive decay, the unstable side of atoms. While all atoms of a particular element have the same number of protons, they can have different numbers of neutrons. These variations are called isotopes. Lab technician, for example, carbon-12, the most common isotope of carbon, has 6 protons and 6 neutrons, while carbon-14, a radioactive isotope, has 6 protons and 8 neutrons. Some isotopes are unstable and undergo radioactive decay. This means they spontaneously emit particles or energy from their nucleus to become more stable. This process is what makes certain elements radioactive. Lab technician radioactive isotopes have various applications, from dating ancient artifacts, through carbon dating, to diagnosing and treating diseases. Understanding isotopes and radioactive decay is essential in fields like nuclear medicine, archaeology, and geology. Section 8. Atoms in action, chemical reactions and bonding. Atoms are not static entities, they are constantly interacting with each other. These interactions, called chemical reactions, are responsible for the vast diversity of substances and materials we see around us. Scientists too, chemical reactions involve the rearrangement of atoms and the formation of new chemical bonds. These bonds hold atoms together to form molecules. Different types of chemical bonds, such as ionic bonds and covalent bonds, result from the sharing or transfer of electrons between atoms. Scientists too, understanding chemical reactions and bonding is crucial in various fields, from developing new materials and medicines to understanding biological processes and the environment. It's the foundation of chemistry and a key to unlocking the secrets of the material world. Section 9. The power of atoms, from energy to technology. The study of atoms has led to profound technological advancements, from nuclear power to modern electronics. Understanding the structure and behavior of atoms allows us to manipulate them for various purposes. Lab technician, nuclear power for example, harnesses the energy released during nuclear reactions, a process involving the nucleus of atoms. Nuclear power plants provide a significant portion of the world's electricity, though they also come with risks and challenges. On a smaller scale, the transistors that power our computers and smartphones rely on the behavior of electrons within semiconductor materials. These tiny devices have revolutionized electronics and information technology, shaping the modern world. Section 10. The future of atomic understanding. The journey into the atom is far from over. Scientists are constantly pushing the boundaries of our understanding, delving deeper into the subatomic realm. Scientists too, particle accelerators like the Large Hadron Collider, allow us to smash atoms together at incredible speeds, creating new particles and revealing the fundamental forces that govern the universe. As we continue to explore the atom, we can expect even more groundbreaking discoveries and technological advancements. From new materials with unprecedented properties to innovative medical treatments, the future of atomic understanding holds immense potential. Scientists too, the atom, once considered the smallest indivisible unit of matter, has revealed a universe of its own. As we continue to explore this microscopic realm, we gain a deeper appreciation for the elegance, complexity, and profound implications of the atom, the fundamental building block of our universe.